So today's lesson is going to be on the analysis of frames. So here are our learning outcomes. Identify and define the components of frame structures. Apply methods such as joint equilibrium, method of sections, and method of moments to solve for unknown forces in frame structures. Create a free body diagram and identify procedures for frame analysis. Now let's understand frames. Frames are structural systems made of multiple pin-connected members designed to support loads. Unlike trusses, which consist of only two force members, frames contain multi-force members, meaning they experience more than two forces at different points. So the visual representation illustrates the concept of forces acting on a frame structure, focusing on two force members, multi-force members, and action-reaction pairs in a free body diagram. So if we look at our image, the two-force and multi-force members, the left diagram shows a frame with a two-force member, AB, and a multi-force member, BC. A two-force member experiences only two forces at its end, which are equal, opposite, and collinear. A multi-force member, like BC, experiences more than two forces, requiring a more complex equilibrium analysis. Next, when looking at action-reaction forces, the right diagram depicts the free body diagram of the same structure. Forces at joint B are labeled as force in member AB and its reaction force. The action-reaction principle states that forces between two connected members must be equal in magnitude but opposite in direction. So free body diagrams is the key to analysis. To analyze a frame, we need to disassemble it into its individual members and draw free body diagrams. This allows us to determine the forces at joints and supports efficiently. So first, we isolate each part. So we're outlining the shape of each member, we're showing all the applied forces and the couple moments, and you're identifying both known and unknown forces using an XY coordinate system. Next, you're identifying the two force members. So the two-force member is a structural element where only two forces act at its ends. Remember that they are equal, opposite, and collinear. Identifying these help reduce the number of equilibrium equations needed. And lastly, you're applying Newton's third law. So forces common to two contacting members have equal magnitude but opposite direction. So in the diagram below, we have the frame of A, B, and C. First, we broke it down into multiple pieces, so member AB is not in equilibrium without hinge forces at B. Internal hinge forces are Bx and By, and there's no moment at a hinge. Next, we have the FBD member of BC. So if there are hinge forces on member AB at B, there must be hinge forces at B for member BC. And lastly, for the hinge at B to be in equilibrium, member BC must exert equal and opposite forces on the hinge as member AB. So now let's get into the example problem for today. So example number 1. The question asks for the frame below, draw the free body diagram of each member. So by inspection, members BA and BC are not two force members. Instead, as shown on the free body diagrams, BC is subjected to a force from each of the pins at B and C, and the external force P. Likewise, AB is subjected to a force from each of the pins at A and B, and the external couple moment M. The pin forces are represented by their X and Y components. So now let's get into the frame analysis procedures. So first, we start off by counting the number of unknowns, given by NU. So this includes all the support reactions and the forces at the hinges. So the equation to solve this is the number of unknowns is equal to the number of support reactions plus 2 times the number of hinges. Next, we determine the number of free body diagrams required based on the required number of equilibrium equations. So to solve this, we need the number of equations to equal the number of unknowns. So recall that the number of equations is equal to 3 times the number of free body diagrams, which is equal to the number of unknowns. Thus, the number of free body diagrams is equal to the number of unknowns divided by 3. Third, we draw the required number of free body diagrams. So this includes the entire structure, we can draw the portion of a structure, or the individual members. Remember to use judgment to decide how many free body diagrams will yield the most direct solution. Lastly, apply the equations of equilibrium to each free body diagram to solve for the unknown joint forces and support reactions. So recall that you may not be able to solve for each force directly, but you'll have to use the system of equations to solve. So some helpful tips in order to solve frames is if a frame has only 3 support reactions, it is often helpful to solve for them first using a free body diagram of the entire frame. Next, look for 2 force members. Identifying 2 force members will reduce the number of unknowns and simplify the analysis. Now let's get some practice by using the frame analysis procedures. So here's example number 2. Determine the horizontal and vertical components of force which the pin at C exerts on member BC of the frame. So first, start off with drawing out your free body diagrams. By inspection, it can be seen that AB is a 2-force member. The free body diagrams are shown as such. Next, we're going to apply the equations of equilibrium. The 3 unknowns can be determined by applying the 3 equations of equilibrium to member CB. So this is, first, calculating the summation of moments about point C is equal to 0. So we're taking the moments about point C to eliminate the reaction forces that are at the point of C. So 0 is equal to 2,000 newtons times 2 meters. So the 2,000 Newton force creates a counterclockwise moment about point C minus the force in members AB times sine 60 degrees times 4 meters. So the force in members AB creates a clockwise moment about point C. So the force in members AB is equal to 1,154.7 newtons. Next, we take the summation of forces in the x direction, which is equal to 0. So this is equal to 1,154.7 newtons times cos 60 degrees newtons minus the force at Cx. So the force in the x direction of C is equal to 577 newtons. Finally, we take the summation of forces in the y direction, which is equal to 0. So this is equal to 1,154.7 newtons times sine 60 degrees minus the 200 Newton force plus the force in the y direction at C. So Cy is equal to 1,000 newtons. In summary, in example 1, we drew out the free body diagrams for the frame. And in example 2, we found that the force in members AB is equal to 1,154.7 newtons. The force in the x direction of C is equal to 577 newtons. And the force in the y direction of C is equal to 1,000 newtons.